We've been starting to look at how to answer probability questions, and at this point, we want to make sure that we understand how to calculate probability for discrete random variables. Now, we want to distinguish here between discrete and continuous random variables. So, continuous random variables are variables representing data sets that we can think of as being continuous. So, think about, for instance, dimensions like length, width, and height, or maybe even area or volume. One common example is the heights of people. We would call the height of people a continuous random variable because, in theory, people can take on any height, at least maybe within a particular range. So we might say that somebody measures 5 feet 6 inches tall, and then another person measures 5 feet 7 inches tall. But we also recognize that there are many people who have some height in between 5'6" and 5'7". We might have somebody who measures exactly 5'6" and a half, or somebody who measures exactly 5'6" and a quarter. And if we go even more granular in our measurement, in theory, we could measure an infinite number of different heights between 5'6" and 5'7". The only thing that's holding us back here is how granular we can get with our measurement. But the concept is that if we had the ability to measure with more and more and more accurate precision, we could find many different heights, an infinite number of heights between 5'6" and 5'7", and so we can define the height of people as a continuous random variable. The same would be true for time. In normal life, we might only be interested in measuring time in terms of maybe seconds, minutes, or hours. But at the Olympics, when we're talking about athletes who race down to the 10th of a second or 100th of a second or even 1,000th of a second, as long as we could continue measuring at a more and more granular level, we could continue to distinguish between lengths of time, and so time would be considered a continuous random variable. Contrast this with the idea of discrete random variables. The key here we want to think about is things that are countable. For instance, number of children in a family. It's impossible for a family to have 2.7 children or 4.2 children. That family is always going to have 0, 1, 2, 3, etc. number of children. The number of children in the family are countable. Or we could think about something like flipping a coin, so coin flips, and the number of heads that we get in those coin flips is always going to be 0, 1, 2, 3, etc. It's impossible if we flip a coin 2 times to get half of a head or 1.5 heads. We're always going to get 0, 1, or 2 heads in 2 coin flips. And there's no in between. Even if we could get more granular with our measurement, it doesn't make sense to say that we get 1.5 heads on 2 coin flips. There's only these discrete values and nothing in between those values. So just think about discrete random variables as countable variables with no logical in-between values. Whereas with continuous random variables, we have, in theory, an infinite number of in-between values. And as long as we can get specific enough in our measurements, we could continue finding more and more in-between values. So with that in mind, what we want to do now is make sure we understand how to do probability calculations when we have a discrete random variable. So let's go back to this idea of the coin flip. And let's say that we flip a coin 1 time. There are only 2 possible outcomes when we flip the coin 1 time. We can either flip heads or we can flip tails. If we think about that in terms of probability, we could build ourselves a little table here, and we could say that the discrete random variable modeling the number of heads that we get when we flip that coin is x. So this variable x here models the number of heads we get when we flip a coin. And if we flip the coin 1 time, there are only 2 possible outcomes. One is we flip heads 0 times. The other is we flip heads 1 time. Since we're only flipping the coin 1 time, there's no way to flip heads twice or 3 times. And obviously negative numbers don't apply here. So only 2 outcomes: we flip heads 0 times or we flip heads 1 time. And then we can think about the probability of each of these outcomes for this discrete random variable x. Well, we would indicate that as the probability of x. And so this value here in our table is the probability that we flip heads 0 times when we flip the coin 1 time. Well, the probability of flipping heads 0 times when we flip a coin once is equivalent to the probability of flipping tails on that coin flip. So that probability is 1/2. the probability that we flip heads once when we flip the coin one time is also, of course, 1/2. So we have a little table here with our discrete random variable x and the probability that we find this particular value of x. Now, if we want to represent that in a probability distribution, here's what that looks like. We could make a probability distribution here. We'll have the values that x can take on along the horizontal axis. And along the vertical axis, we'll have the probability that that particular value of x occurs. So here's what the distribution would look like for one coin flip. It's this distribution here. We see along the horizontal axis that in one coin flip, x, the number of heads that we get when we flip a coin one time, can only take on the values 0 or 1. With one coin flip, it's only possible to flip heads 0 times or 1 time. So these are the only values we have along our horizontal axis. We've put our vertical axis in units of 16ths so that we can expand on this graph as we add more flips to our table here. So if we think about each unit here along the vertical axis as being out of 16, then 8 divided by 16 is the same as 1/2. So our probability right here is 1/2. Our probability at 4/16 is 1/4. Our probability at 2/16 is 1/8. So since we know from our little probability distribution table here that the probability of flipping 0 heads is 1/2, we've indicated that here with this bar that extends up to 8/16 or 1/2. And then same thing here, the probability of flipping heads one time is also 1/2, so we have that represented with this bar here. This is what probability looks like for a single coin flip, with the discrete random variable x representing the number of heads that we flip on that coin flip. If we now add a second coin flip to this scenario, now we're going to say that we flip a coin 2 times. Well, we have to now account for all of these possibilities. Notice what we did here is that we started with our original single coin flip, and we said that on our first coin flip, we're either going to get heads or tails. Now, on our second coin flip, we could get heads after flipping heads on the first flip, or we could get heads after flipping tails on the first flip. But we can also have the scenario where we flipped heads and tails on the first flip, but then tails on the second flip. So what was 2 possible outcomes with one coin flip is now 4 possible outcomes with 2 coin flips. And if we express that probability in a table, here's what the table looks like. So again, we still have the same discrete random variable here, where x is the number of times that we flip heads. Now that we're flipping the coin 2 times, we can flip heads 0 times, 1 time, or 2 times. And the probability that each of these outcomes occurs is given here by the probability of x. We see that flipping heads 0 times only occurs in this scenario here where we get tails, tails. So there's a 1 in 4 chance that we flip heads 0 times. The probability that we flip heads 2 times occurs 1 out of 4 total possible outcomes. And that's here in this first scenario where we flip heads and then heads again. And there are 2 different ways that we could flip heads 1 time out of 4 possible outcomes. That's when we flip tails then heads or heads then tails. So the probability of flipping heads 1 time is 2 matching outcomes out of 4 total equally likely outcomes. So we have here our probability distribution. And if we graph that, here's what that looks like. Now in our graph, we can flip heads 0, 1, or 2 times. We can see that the probability of flipping heads 0 times is 1/4, so we've sketched that in. The probability of flipping heads 2 times is also 1/4, so we sketch that in. And the probability of flipping heads 1 time is 2 out of 4, or 1/2, so we sketch that in here. And now this is the probability distribution for the discrete random variable x, where x is the number of heads that we flip when we flip a coin 2 times. So we're starting to get an idea here. Let's look quickly at what happens when we expand this to 3 coin flips and then 4 coin flips. So if we expand to 3 coin flips, here's what our table looks like now. We kept everything we had before. We said that this was our first coin flip in white, in blue was our second coin flip, and now in red, we've attached an extra flip to those first 2, and we've said that on this third flip, we flip heads every single time. But of course, we also have to account for the same set of the first 2 flips, but where on the third flip, we flip tails every time. So now with 3 coin flips, our 4 possible outcomes expands to 8 possible outcomes, which means that our probability distribution table, if we're flipping the coin 3 times, we can flip heads 0, 1, 2, or 3 times. There are 4 different possible outcomes here. And if we just count up here the number of times that each of those can occur, for instance, here, the only time that we flip heads 0 times is when we get tails, tails, tails. So out of these 8 possible outcomes, only one of them is flipping heads 0 times. And so the probability there is 1/8. Same thing here. The probability of flipping heads 3 times is when we get heads, 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 no tails. We see that here. That's 1 out of all 8 of these outcomes. So the probability there is 1/8. So we build out this table. And now if we sketch this distribution in our graph, we see that it looks like this. What we're hopefully noticing at this point is that the distribution is always higher in the middle and lower around the edges. For all 3 of these scenarios where we were flipping a coin 1 time, 2 times, 3 times, the distribution has roughly the same shape every time. And if we flip a coin 4 times, so we add to this, we had our first flip, second flip, third flip. Now we add a 4th flip. So for all these scenarios here, we say that the 4th flip comes up as heads. And then we duplicate this whole set and say that the 4th flip this time comes up as tails every time. So our 8 possible outcomes has now doubled to 16 possible outcomes. And our little probability distribution table looks like this. When we flip a coin 4 times, we can get 0, 1, 2, 3, or 4 heads. If we just count out of all 16 outcomes here, the number of times that we get 0 heads, 1, 2, 3, or 4 heads out of the 16, we can fill out here the probability of this specific number of heads. And if we sketch this distribution into our graph, it looks like this. And now we're really starting to see this sort of triangular shape of the probability distribution of this discrete random variable. And of course, if we kept going, this distribution would get more and more and more fine, more and more accurate, and we would see that the general shape of the distribution would look something like this, and it would approximate this curve more and more accurately as we add additional coin flips to our distribution. Now, all of that to say, with this idea of a discrete random variable and its probability distribution, we want to recognize that discrete probability is just like any other probability in the sense that the probability of the discrete random variable is always going to sum to 1 or 100%. Remember earlier, we said that probability was always defined between 0 and 1. And we can see here that all of these probabilities, all of these right-hand columns in each of our 4 tables here for 1 coin flip, 2 coin flips, 3 coin flips, and 4 coin flips, all of these probabilities are between 0 and 1. We have our smallest probability here at 1/16th, all the way up to our highest probability of 1/2. All those values are between 0 and 1. And each of these right-hand columns sums to 1. 1/2 plus 1/2 is 1, which we could also call 100%. We could call each of these 1/2 values 50%. So 50% plus 50% is 100%. Same thing here, 1/4 plus 2/4 plus 1/4 is 1, or 100% if we add up 25%, 50%, and 25%. And that's going to be true for all of these. You'll see here that this adds up to 8/8, or 1, and that this adds up to 16/16, or 1. So that concept still holds with discrete random variables. What we want to be able to do now is talk about how to calculate the expected value of a discrete random variable, and we also want to be able to look at variance and standard deviation for a variable x like we've been talking about. So expected value, or that long-term average, is like what we talked about before when we looked at experimental versus expected probability. And to calculate it here for a discrete random variable, so let's take this scenario where we have just 1 coin flip. When we have a discrete random variable, we have to take what's essentially a weighted average. So we look at here these different countable outcomes, x. We say that when we flip a coin 1 time, we can either flip heads 0 times or 1 time. And the probability that each of those things occurs is 1/2. So we take the possible outcomes here, 0 and 1, and we weight each of them by their probability 1/2. And when we do the math here, we get 0 plus 1/2, or 1/2. And what this tells us then is that when we flip a coin one time, the expected value for the number of times that we flip heads is 1/2. So it's almost saying that we can expect half heads on our one coin flip, which of course doesn't make sense. When we flip a coin one time, we know that we can only flip heads 0 times or 1 time. We can never flip it half of a time. But this is what the expected value is saying. And of course, in a way, that makes sense, because if we're trying to represent the number of times we should expect heads on one coin flip, even though we know the only outcomes are 0 or 1, it would be wrong to say that our expectation on one coin flip is always 0 heads, or that our expectation on one coin flip is always 1 heads. We can't really use either one of these values. We have to go in the middle because, as we already know, we've looked at it already when we talked about probability, and we also should just know this intuitively. We should expect to flip heads about 50% of the time, and so if we're flipping a coin only one time, in this theoretical world here, we should expect half of a heads on that one flip. Let's look at what happens though when we flip a coin 2 times, 3 times, 4 times to our expected value. So when we flip a coin twice, our expected value is this. We have all of our different outcomes, 0, 1, or 2 heads, and we weight them with their associated probabilities. And so when we do the math here, the result is 0 plus 1/2 plus 1/2, or 1. And this then should make a lot more sense to us, because we're saying if we flip a coin 2 times, we expect to flip heads 1 time. That is our long-term average. That is our expected value for this discrete random variable. And of course, that makes sense to us. What happens though when we flip a coin 3 times? This time, we can flip heads 0 times, once, twice, or 3 times. We weight these values with their associated probabilities, and we get 0 plus 3 over 8 plus 6 over 8 plus 3 over 8, and we get 12 over 8, or 3/2. 3/2, or we could think about this as 1.5. So what this is saying is that if we flip a coin 3 times, we should expect 1.5 heads, which of course, in the context of the discrete random variable, where we know it can only take on the values 0, 1, 2, and 3, 1.5 heads doesn't make sense. But as a long-term average, of course, it does make sense, because we know that flipping a coin, we should always get 50% heads, 50% tails, as long as we're taking a big enough sample, as long as we're flipping the coin enough times to get a good long-term average. And so if we're flipping the coin 3 times, of course we should expect 1.5 heads. And then the last one, hopefully you can already guess by now, when we flip the coin 4 times, we see that we have all the possible outcomes, 0, 1, 2, 3, or 4 head flips, and we weight them with their associated probabilities, and we get 0 plus 4 over 16 plus 12 over 16 plus 12 over 16 plus 4 over 16, and we end up with 32 over 16, or just 2. And that makes sense because when we flip a coin 4 times, we should expect long-term, on average, heads to come up 2 times. So in a way, all of this should make sense, but the real unlock here shows up in these odd values where we're flipping a coin 1 time, or we're flipping a coin 3 times. The even values, where we're flipping a coin 2 times, 4 times, 6 times, etc., those make sense to us. We get these nice whole round numbers where the expected value is 1, 2, etc. But what these odd values show us is that we can get an expected value, which is in fact our mean. We call this the mean of the discrete random variable x. This is mu sub x, and it represents the mean, and in the case of a discrete random variable, it's the expected value. But these odd values show us that the mean of a discrete random variable can turn out to be a value that is in between the discrete values that the variable can actually take on. So even though here this variable can only take on values of 0 or 1, we find a long-term average of 1/2. Even though here with 3 coin flips, the discrete random variable can only take values of 0, 1, 2, or 3, this expected value formula, this idea, shows us that we can still calculate a mean even for a discrete variable, where that mean ends up being a value in between the values that the variable can actually assume. So even though here we can only find values of 0, 1, 2, or 3, the mean is 3/2. The mean is 1.5, not any of these values at all. So we understand now the idea of the probability that a discrete random variable takes on a particular value. We've seen what that looks like in terms of the distribution, the probability distribution of that discrete random variable. And we understand now how to find the expected value, or the mean, of that discrete random variable, and that the mean may be a value that is between some of the values that the discrete random variable can actually assume. So now that we have this mean, this expected value, we want to just talk about the variance and standard deviation of a discrete random variable. And this is going to be our variance formula for a discrete random variable. These x sub I values are just the individual values of the discrete random variable. In this case, with 4 coin flips, that's 0, 1, 2, 3, and 4. And then you'll see here the probability of each of those values. So this little probability distribution table gives us all the information we need to substitute for x sub I and the probability of x sub I. And then mu here is the expected value that we looked at earlier. It's the mean. And so you can see what we're doing is just finding the difference between the value of the discrete random variable and the mean, and then we're squaring that distance. Squaring the distance is going to guarantee that we get a positive outcome here for this x sub I minus mu quantity squared. So this value is always going to be positive. And then we're going to multiply that by the probability over here, p of x. And we're going to do that for each one of the possible values of x. And then we're just going to add them all together. That'll give us the variance of this particular discrete random variable. So let's do that for the discrete random variable x here, where x models the number of times we flip heads when we flip a coin 4 times. So if we substitute, our variance here will be our first value of x, which is 0. So we'll say 0 minus the mean. We calculated the mean down here, and we said that that was 2. So we get 0 minus 2 quantity squared times the probability of getting 0 heads when we flip the coin 4 times, which we know is 1 out of 16. So we multiply this by 1 over 16, and then we keep going until we get to the bottom of our probability distribution chart here with x equals 4. So here, our next row, where x is 1, we flip heads 1 time, we get 1 minus 2 quantity squared times 4 over 16. And then we add to that, when x is 2 here, 2 minus 2 quantity squared times the probability there, 6 over 16. And then we add to that 3 minus 2 quantity squared multiplied by 4 over 16, and then the last row here plus 4 minus 2 quantity squared times 1 over 16. And of course, we're doing this by hand just so we can see the math, but all modern scientific calculators and computer programs will calculate a variance for you based on this kind of probability distribution. So in reality, we're not ever doing this math by hand, but we just want to see what's actually going on behind the scenes so we understand what's happening. So this is the manual calculation. And when we actually do this here, we get negative 2 quantity squared is 4. 4 times 1 over 16 is 4 over 16. 1 minus 2 is a negative 1. Quantity squared is positive 1. So plus 4 over 16. 2 minus 2 is 0, so that whole term is going to drop away. 3 minus 2 is 1, squared is 1, times 4 over 16 is 4 over 16. And then 4 minus 2 is 2, quantity squared is 4, times 1 over 16 is 4 over 16. We end up with 4 plus 4 plus 4 plus 4 is 16. So we get 16 over 16, or 1. And so our variance for this particular discrete random variable, the number of heads we flip when we flip a coin 4 times, is 1. And as we already know, the standard deviation we can find by taking the square root of variance. So the standard deviation of this discrete random variable x will be the square root of variance, or the square root of 1, or just 1. Of course, these numbers worked out really cleanly for this particular variable. That won't always be the case. But now, even though we started with a discrete random variable, we can say that this particular discrete random variable x has an expected value, or a mean, of 2, that it has a variance of 1, and a standard deviation of 1. And now we can use all this information to answer probability questions about the discrete random variable, like what is the probability that we get more than 3.25 heads when we flip a coin 4 times, or the probability that we flip some number of heads between 1.5 heads and 2.7 heads. And we're not bound by these discrete values. We've sort of, with these calculations, transformed what would otherwise be a completely countable discrete variable into something where we can examine the values in between.